Okay, so we're going to make a couple of assumptions. I'm going to assume that we didn't do this problem just to kind of go over it and kind of get our brains working again. So in the case of nicotine, right? Nicotine is 74.1% carbon. It's 8.64% hydrogen and 17.3% nitrogen. What is its empirical formula? Okay, so you guys remember the empirical formula is going to be the smallest form that we can get for that chemical compound in terms of their the quantity of each element, right? So we know that we have to do what first, and what can we assume if we have 74.1% carbon, 8.64% hydrogen, and 17.3% nitrogen? How can I kind of get this done?
The majority is going to be carbon.
So we know that the majority of it is going to be carbon, right? And we know that all of it together makes up our nicotine. So if we just kind of do something kind of simple and make an assumption that we have 100 grams of nicotine, then we know how many grams are going to be carbon.
74.1.
So that means that 74.1 is going to be carbon. How many of it is going to be hydrogen?
8.64.
8.64. And how many is going to be nitrogen?
17.3 grams.
Okay, so we know we're going to be comparing the mole ratios, so the moles of each one to each other, right? Because that's quantity. So we know how many I have. You guys know the difference between quantity and mass, right?
Yes.
So like, for instance, I weigh 220, but there's only one of me, right? So mass, my weight, and how many there are of me is quantity, okay? Okay, so we want to sit there and compare the quantity. So we want to use moles as means to compare that quantity. So first thing I want to do is to do what?
Find the molar mass of each element.
Find the molar mass of each element. What is the molar mass of carbon?
12?
What was that?
12?
Or what is the 12? Yeah. So we know that it's 12 grams per 1 mole. So our grams are going to go on bottom, 1 mole on top. And that's going to give me
6.175 moles.
okay. Hydrogen. What is the molar mass of, or the atomic mass of hydrogen?
Is it going
One.
to stay the same because it's just one?
Mm-hmm. And nitrogen.
14.
So 1.23 mole.
And I know we're kind of, a little foggy, but if I was making comparisons, right? So if I wanted to sit there and get a whole number, because we're basing everything on whole numbers, we can't have these fraction numbers, because you can't have a half of a molecule. You only can have a whole of a molecule, right? Like, same thing, we can't have half of you, we can only have a whole of you, right?
So would it be 6, 9, and 1 instead of those numbers?
So no, it wouldn't be 6, 9, and 1. We want to take our smallest number, right? And divide by the smallest number. Because that gives us reference to each other, right? So what is our smallest number? Which has the
1.23 moles of nitrogen.
1.2 moles of nitrogen.
Wait, why are we dividing the nitrogen mole by the rest of them?
Because it is the smallest number, right? Smallest number of moles. So we're using that as our reference because we're comparing them to each other, right? And so we want to compare them so that they're a whole number. And the only way that we can do that is by dividing by that smallest number, try to get as close to the whole number that we can get. Does that make sense, Brittany?
A little bit, I'm watching.
Okay. So in this case, if we divide nitrogen by itself, it's going to be 1 nitrogen. If we divide this hydrogen by 1.23, what do you guys get?
7.
Okay, so we have 7 hydrogens. And then if we divide the 6.175 divided by 1.23,
5.
so we end up with C5 H7 N1. As our final empirical. Okay, piece of cake. Okay, so again, if we go through that process, we're comparing moles, right? Moles gives us quantity. So we know that this is like 1.23 moles. So we want to divide it again by that smallest number because that gives us reference of everything compared to that one in terms of a 1 unit of that particular one, right? So we got 1 unit for nitrogen, we have 7 for hydrogen, and we have 5 for that carbon. Okay. Are you good, Christina? Yes,
Yes.
no, maybe? Good. Okay. Okay, so if we have to determine the molar formula, the empirical formula is that the lowest, basically the lowest integer that you can get, right? The lowest common denominator taken into consideration. The molecular formula is the actual chemical formula that we're using. So sometimes what we'll do is have to do both. We have to determine the empirical formula, then use that to determine our molecular formula. Okay, and I'm going to give you 2 problems where we're going to do this. Helen asked, what is the value of 1 mole again? So the value of 1 mole is like a mole is kind of like a dozen. So, but it, instead of being 12, a dozen is 12. A mole is 6.022 times 10 to the 23rd of anything, right? It could be atoms, it can be molecules, it can be ions, it can be electrons, it can be anything. Okay, does that make sense?
Yes, thank
So,
you.
yeah, and as Christina was saying, we know that if we're talking about a particular atom, we could sit there and say 1 mole is equal to the mass associated with that atom, right? So 1 mole is 1 mole of carbon is going to be 12 grams, or we could say the molecular mass of carbon is 12 grams. Okay, so let's do this problem here, and then we'll do one of your homework problems. So a compound with the empirical formula C2H5 has a molar mass of 58.12 grams per mole. What is the molecular formula? So in this case, we've already figured out the empirical formula, and we're given the empirical formula. So at this point, it's pretty simple. All you would do is take your empirical formula, you calculate its molar mass. So what is the molar mass of C2H5? How would I calculate that?
Carbon weighs 12.
Okay, and how many
12
carbons do we
times
have?
Two?
Two carbons.
That would be
So-
24.
24. Right?
Okay, so that's 24. Okay, hydrogen. How many hydrogens do we have?
5.
5.
Hydrogen weighs
1.
5 times 1.
5.
So that's 29 grams per mole. So, oops. We take this mass, which represents the mass of the molecule that we're looking at. So that's 58.12 grams per mole. We divide it by the mass of the empirical formula. That's 29 grams per mole. So the factor that we multiply by is going to be 2, right? And again, this has to be a whole number, a whole integer number. So in this case, the molecular formula would be C4H10. Okay, questions? Concerns?
I know, pretty straightforward to me.
Okay, good. Okay, so that's chapter 7. Let's see. Gonna pull up one of your homework questions, and then we're gonna work through that. A 5.13 gram sample compound that contains only hydrogen and sulfur was combusted and yields 10.0 grams of sulfur dioxide and 2.81 grams of water. The molar mass of the compound is 68 grams per mole. What is the compound's molecular formula? Okay. So if we take a look at this problem here, this problem tells us a couple of things. One thing, it tells us that we have a compound that is composed of hydrogen and sulfur. We don't know how much hydrogen we have. We don't know how much sulfur we have. But we know that when it does a combustion reaction almost always requires oxygen because oxygen is needed to keep the fire going. It's going to yield sulfur dioxide plus H2O. So our hydrogen, all of our hydrogen that's in this compound is going to be going over to water, and all of our sulfur from this compound is going to be going to the sulfur dioxide. Okay, so we can kind of use this as reference to what we're working with. Okay. We don't know the chemical relationship between this guy because we don't know what these compounds are, but we know that we have this guy. So we're going to kind of use this in a tricky way, right? So we know that we have 10 grams of sulfur dioxide. We know that all of the sulfur is going into our compound. So if we change our sulfur dioxide to moles, right, we can compare the number of moles that are in sulfur dioxide. So how many moles of sulfur are there in sulfur dioxide? So how many moles of S are there in SO?
So is that 32?
What was that?
Would that be the 32? Like, would you go off of?
Well, yeah, we're going to eventually get to the grams, but that grams is not moles, right? So in this case, we're talking about quantity, right? So for every 1 mole of sulfur dioxide, I'm going to have 1 mole of sulfur. For every 1 mole of sulfur dioxide, I'm going to have 2 moles of oxygen. Does that make sense?
Yes, because there's
Yes.
2 oxygen versus the one.
Yeah. So the first thing that we want to do is change our sulfur dioxide to moles, so we can do that mole relationship, right? Okay, so what is the molar mass of sulfur dioxide?
The 32
So sulfur is 32.
together, sorry.
Yes.
64.
64.
Okay, so altogether 64. So it's 64 grams of sulfur dioxide for 1 mole. And we know that's because sulfur was 32. We have 2 oxygens. 2 times 16. Okay, so that's 1 mole of sulfur dioxide. Now, if we look at the relationship between the number of sulfurs that we have in sulfur dioxide, for every 1 mole of sulfur dioxide, we're going to have 1 mole of sulfur. So for every 1 mole, one mole of sulfur. Okay, so then this is going to give me my moles of sulfur. So if we do that math, what did you guys get?
0.156.
You get 0.156.
How many sig figs, Dr. Henry?
Tell me.
Well, there's 3, but
That's right. So then, because this is the only thing, in this case, we have 3 sig figs that are being introduced. When we calculate the molar mass, we don't use that to calculate the sig figs. Right?
Okay.
Okay, so we have 0.156 moles of sulfur. Now, what about water here? So we have 2.81 grams of H2O. Okay,
Then you put the 18 grams of H2O on the bottom.
okay. One mole on top.
Or the mole. And for every one H2O moles, there's two moles of H, right?
That's
On the
right.
top.
That is correct.
Mhm.
Okay, what did you guys get?
0.312.
Okay, so what number is smaller?
The top one.
Okay. So we divide everything by that number, which is 1.56 moles. Okay, so we get 1s, and if I get my math right, 2 h's.
So it should be two H2S.
Okay, so the empirical formula is going to be 2H2S. Yeah. Okay, so now we need to calculate the molecular formula. So what is the molar mass of H2S?
That's the 18, right?
34.
Oh, no, not sorry, not 18.
Yeah, so it'll be 34 because we know that S is 32.
That's 2 plus the 1.
32 plus 2 H's. No, H is 1. So it's 34 grams per mole. So if the molar mass of the molecular formula is 68, we have 68 grams per mole divided by that 34 grams per mole. It's going to equal
The 2.
So then,
Oh, then you have to go back and multiply it to H4O2.
no, you multiply it by
Oh,
this.
not that one. I meant that's the one I meant. The H2 and the S.
So it'll be H4
S2.
S2.
Wait, this is gonna screw me up. These steps. Eee.
What was that?
I said the steps. This I'm gonna get to like the H2S, and I'm like, oh yeah, I got it. I'm there. And then I'm like, why is it wrong? I'm gonna that I need to notate to solve the step.
Yeah. So if they're asking you for the molecular formula, you have to take that extra step, right? And then sometimes what they'll do, rather than giving you the molar mass, they'll say the molar mass is between this range and this range. So then you have to figure out, okay, what number can I multiply my empirical formula that will be in that range? Okay. So, and actually there's an experiment that we had done when I was in school, and we would take a sample, we would get the empirical formula. So we'd get the quantity relative to each other, how much was there. And then that would give us the empirical formula. And then we did this experiment where this was a mole and of that compound. And so we would get the molar mass of that as well too. And then we would have to use that to sit there and calculate, go back to that whole thing. So this is something that is actually used mainly in forensics and stuff like that, or analytical chemistry.
Is this essentially, is this kind of, because okay, I'm sure I'm not the only one that feels this way. Is this the same kind of stuff that we're supposed to be doing for the lab, like in this same kind of like way?
Sort of, yes, yes. So you're using some of the components, that whole concept of finding the molar mass, and then in your context, you're figuring out what is the limiting reagent for that, right? Don't worry about it. We'll get into it. Hopefully we'll get to it today. If not, we'll definitely get to it on Wednesday. I mean Thursday. Okay. Questions?
Well, I was gonna say, if you can give us an example of how to do the lab.
Okay. Sure. It's going to cost you though.
How much?
15 minutes of your time.
Okay.
Okay. Are you guys ready? When I clear this, can I clear it?
Yes.
Okay. Okay, so let's talk about your lab, since you guys are asking about the lab.
Is moles only relative with gases? Like this whole
No, moles are relevant to everything. Again, moles make reference to quantity. It's just masses amount of quantity. It doesn't have to be gases. It could be solid. It could be liquid. But it just deals with the quantity of molecules that are in that substance, right? Okay. Okay, so in your first balloon, you guys put in 1.5 grams of the 1.5 grams of what was it? Sodium bicarbonate. Okay. Is that true?
Yes, it is.
Okay. So we are reacting sodium bicarbonate, NaHCO3 plus acetic acid. And I have it written this way, H2, H3, O2. So that's acetic acid. And it's going to make H2O liquid plus CO2 gas plus sodium acetate, NaC2, H3, O2. Okay. So is this chemical equation balanced?
no. All right.
It's not. How do I determine if it's balanced?
Write it all out.
Okay. So what do you mean by that?
It is balanced.
We look at our Na, we look at our H's, we look at our C's, and we look at our O's, right? So how many O's do we have over here on our reactant side?
We have 5.
We have 5 O's. How many carbons?
We have 3.
And how many hydrogens?
We have 4, 5.
5.
And sodium,
1.
okay? On our product side,
We have
1.
1 sodium. We have 5. We have 3,
3.
and we have 5.
okay? So we just confirmed that it's a balanced equation. Anytime you're doing chemistry, you always want to confirm that it's a balanced equation, right? Because otherwise you're hurting yourself, okay? So are you good so far? Everybody's good there? Okay, so now, as Brittany was saying, this is kind of like what we were doing, with the lab itself, right? So what you guys were doing prior in terms of changing things into moles so that we can get a mole to mole ratio of things, this is what you're going to be doing in this case, okay? So we got to erase this since we know that it's balanced. So can I calculate the molar mass of sodium bicarbonate? So what is the molar mass of sodium bicarbonate? This compound right here.
You gotta add it all up.
I have to add it all up. Okay, sodium. How much does sodium weigh?
23.
My age. Hydrogen.
Just the 1.
It's just 1. And then carbon.
12.
And oxygen.
That'll be 48 because there's 3.
Okay, so 3 times 16.
The 48.
So if we add them all up, 48 plus 12, I believe that's 60. That's 84
I think so.
It is.
grams per mole. Okay, so then I want to get rid of grams so I can get moles. So I'm going to put the 84 on the bottom.
So to figure out all of them, are you gonna just do the same kind of like thing 3? Yeah, because when you do this, right, and you're gonna write 1 mole on the top, 1 mole NaHCO3 over the 84 grams. If you wanted to do the next side to find 1 mole of NaHCO3, if you wanted to say find the carbon, you'd have to put just the carbon up there, right? Like you have to do them separately or no?
Well, you don't have to. Okay, so if we were trying to find the empirical formula of something, we would have to do them each element independently. But if we're trying to find, let's say, a specific chemical, then we just have to look at that particular chemical. Let me show you. Just to take a moment first, okay? And then I'll explain it here in a second, okay? So let me finish writing this down so, our viewers at home will be able to sit there and understand what we're doing. Okay, so what Brittany is saying is, she was like, so when we were doing the empirical formula, we started out with that compound and we found out for just carbon, right? Well, yeah, we could do that, but we can also do it in terms of the compound itself. So in this case, we're interested in the compound, not just carbon, right? Because in this context, we have carbon coming from 2 places. We don't need just carbon. We want to know how much carbon dioxide we're going to be making, right? So if we look at the relationship between sodium bicarbonate compared to carbon dioxide, what is the coefficient in front of that sodium bicarbonate? And what is the coefficient in front of the carbon dioxide?
Are they both 1?
They're both 1. So it's a 1-to-1 ratio, okay? So then I could say for every 1 mole of sodium bicarbonate, I'm going to get 1 mole of carbon dioxide. Does that make sense?
Oh, because it's quantity. Yeah.
That's right. So that's why it's important that you guys understand that we're talking about quantity, right? Okay, so then this would give me my moles of carbon dioxide. Who's going to do all the hard work for me?
It's gonna be 0.018.
0.018 moles.
Of carbon.
Okay, so that's the first part, right? So you're going to calculate how much carbon dioxide you're expecting to get. Now, this here is called your theoretical, right? That means that in theory, if everything works out, and if we have unlimited amounts of vinegar or acetic acid, then I should get a complete reaction and it should go all to this amount of carbon dioxide if I have 1.5 grams of sodium bicarbonate. Does that make sense?
Yes.
Okay.
So Dr. Henry, just so that the reactant product on the top, is that exactly what we're actually using on our lab?
Yep. That
Okay.
is, this is the exact chemical reaction that's happening. So this here represents, like I said, again, our theoretical. Okay, so this is our theoretical. Okay, now our actual is what we're measuring with the balloon, right? So if you guys did it, you had your water bottle and you had your balloon in there, and you know that you put in 80 mils of solution in it, right? So if your water bottle holds 500 mils, so here's my water bottle. Okay, this is my water bottle. So this water bottle had liquid in it up to 80 mils, because we put 80 mils of vinegar in there. A water bottle typically has a volume of 500 mils, a 16-ounce water bottle. Okay, so now if I fill this up with gas and then I also fill up that balloon, right? So I'll subtract that 80, although I'm using some of it, but we're going to replace that with water. So you're going to end up with, what is that, 420?
This 420.
Okay, Sal, no jokes. So we're going to end up with 420, 20 mils of volume. And you know that volume kind of represents space being occupied, right? And then we're going to also have that volume that we're going to have in the balloon. So did you guys have a diameter in your balloon?
Yes.
Yes.
Okay. So can you guys provide me with your diameter? Somebody. For the 1 point. Say it again, please.
5.3.
5.3. And what units were that?
On centimeters.
Centimeters. Okay. So if your diameter was 5.3, so we're saying our diameter equals 5.3. We know that when we're calculating volume of a sphere, and we're going to assume that your balloon was a sphere, it's 4/3
Times pi.
pi r cubed. Okay, we know that diameter equals 2R, right? Or we could just say R equals diameter divided by 2. Okay, so my R in this case is going to be
2.65.
okay, so we'll say 2.6 because we know that if it's 65, there's 2 sig figs in this case,
Okay.
right? And
Yes.
that 5 isn't exact, so. Okay, so then we plug that R in here. So we get our volume is equal to 4/3 pi 2.6 cubed. And we know centimeters are going to be cubed as well. Okay, so you're going to end up with, who's done the math? Who's quick on the gun?
The pie part always throws me off. So
What was that?
the pie part always throws me off. Like I always don't know what to do with it.
It's a symbol. It just means 3.14, you know. So you just look for the pi symbol on your calculator.
I don't think I have one.
Everybody has one.
3.62.
You got 3.62
Yes.
or 73.62. Okay, so if I have 2 sig figs and I got something like this,
74.
okay, so 74 cubic centimeters. Okay, Brittany asked, where does the 4/3 come from? So that's the equation for the volume of a sphere. So 4/3, if you actually go through and there's a calculation that you can actually do and you end up getting 4/3. Just remember the equation that for the volume of a sphere, it's going to be 4/3 pi r cubed.
That's Brianna asked.
I'm sorry, Brianna, not Brittany. Sorry, Brianna. Okay. How are you guys doing so far, right? So now we have cubic centimeters, but we know that we had gas occupied in that in milliliters. How do I change cubic centimeters into milliliters? What
It's
is the
1 to 1.
conversion factor?
Oh, it's 1 centimeter
It's-
cube equals 1 ml.
So it's
milliliter.
1 to 1, right?
Yes.
So 1 cubic centimeter equals 1 milliliter. So we get 74 milliliters. Okay, so then my total volume is going to be equal to, it's almost at 500, isn't it? It's what is it? 494. Okay. Let's put decimals here to make it good. Okay, so that's my total volume. Okay, so you're asking me at this point, you're like, okay, so we've calculated this volume. Man, what are we going to do with that volume, right? So we're going to use that volume. Do you mind if I go to another page? To make more room? So we're going to use that volume for this equation. PV equals nRT. So when we work with gases, let's talk about gases. This is an opportunity to kind of get ahead. So when we work with gases kind of have this special relationship, right? And the special relationship about gases is called the ideal gas law. So there's this equation, which is this equation. Pressure times the volume equals the number of moles times a gas constant temperature, okay? So I'm going to write all of that out, type it out for you, so you guys remember. So P equals pressure. V equals volume. N equals number of moles. R equals gas constant. Ideal gas constant. I'm going to give you the value for that. You should have it on your conversion sheets, one of your conversion sheets. And the units are, I'll write down the units by hand. It's big. Here in a second. And then T is temperature. Okay, so the units for the ideal gas constants are atmospheres. And so we want to make sure that our units are harmonized, meaning that they're the right units. Atmospheres, liters divided by moles Kelvin. Okay, so we're going to make an assumption that our temperature is equal to 22 degrees Celsius. Okay, which we have to convert to Kelvin because that's what our R is in. So how can I convert 22 degrees Celsius to Kelvin?
Plus 270.
Add
So we just add 273. So that's 295. Okay, we're going to make the assumption that our pressure right now is 1 atmosphere, 1 ATM. Okay, we're going to have our volume from what we just calculated. And I believe, what did I calculate my volume to be? It goes 494.
yes for 94.
And that's milliliters, right?
Yes, milliliters.
So we have to convert that to liters. So how do I convert 494 into liters?
Divided by 1,000.
So I divide it by 1,000.
That would be 0.494 liters.
Zero 0.494 liters. Okay, so then I need to solve this equation for the number of moles, because this will give me the number of moles of carbon dioxide, which is the only gas in that chemical equation. So you know all your gas is coming from there. So if we solve for N, then we'll get N equals PV over RT. So funny. Okay, so then it's just plug and chug. What was our value for P? 1 atmosphere. Our value for V
0.494 liters.
Our value for R,
The 0.821. Times the 295.
and then times 295. Okay, so we make sure our units are canceling out. So those kelvins are going to cancel out. Those moles, oops, I'm not going to cancel out moles. We leave the moles. ATM, liters cancel out. Okay, so then our value is going to be for N.
Would it be? Do you have to times 295 or?
Yep, no, you're dividing it by 295.
Okay.
Yeah, so you're going 0.49 divided by all the stuff at the bottom here.
How come it's not 0.0203? Oh, not 03, but 04.
Oh, you're right. Okay, so go back to the other page. What do we get for our not too bad.
Centimeters cubed?
What was that? No, not our centimeters cubed. But this is our theoretical right here. Theoretical.
Mhm.
And then this was our actual. So in this case, our actual is bigger than our theoretical, which is rare. It normally doesn't happen that way, right? So that probably meant that we may have gotten carried away with that measurement a little bit, but that's not too bad though, because you had, so actual, I can spell. And then our theoretical was
The 0.018 moles.
yeah. Okay. And so the way that we calculate our percent yield, in this case, we're going to have a higher percent yield than what we should have, because it's actual over theoretical times 100. What do you guys get? Thank you, Christina. So you mean 113, right? Because we multiplied by 100.
So this would be 113%. So whatever the decimal we get, just times that by 100.
Yep.
Okay.
And that's going to give you a percent yield. Okay. So that meant that we got more than what we were supposed to get. So that could be because, again, these were all estimates based upon our teaspoon. So it could be that that Daisy's teaspoon is bigger than my teaspoon when I was actually using it to weigh the amount a fourth of a teaspoon is, right? Okay.
I'm glad we went over this today.
Yeah. Okay. So you guys got that, right? Yes, no, maybe?
Yes.
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 Okay. So you're basically going to be doing that 6 times, right? For all of these.
Fun.
Okay. So, but then that is just half of it, right? Because then you also have to tell me which one is going to be limiting, right? Because we're putting in 2 different things. So we need to talk about that vinegar. So vinegar was that other, oh, let me go back.
But for the limited part, aren't we just telling you that based off of our numbers? Like, aren't we just off of the experiment? We're just telling you that, or
Okay, yes, you're telling me based upon the experiment, but you also need to show me based upon theoretical, right? So theoretically, you can figure out what's going to be limiting, right? Can you not? Your eyes are going to be showing you, okay, how do I say it? Hold on. Can you guys see this?
no, your screen's swallowing it.
It's
No,
too
because
small.
of the
Okay.
background. Yeah.
Okay, so it says, my shirt says, I can't believe what you say because I see what you do, right? So you guys are often, you don't believe what I say because you don't see what I do, right? You can't see what I do. Here's an opportunity so you can actually see it with your own eyes. I want you to believe what I say by actually doing it. So your experiment is going to show you that concept of limiting reagents, right? And then you guys are going to sit there, you're proving it by what you see, and then you're also going to prove it by the calculations. Does that make sense?
Yes.
Yeah.
So if I remember correctly, your balloons blew up, did they not?
Yes.
And you guys, you had your first one, it got so big. Then your second one got a little bit bigger. And your third one got a little more bigger. And then your fourth one kind of stayed the same, right? And then your fifth one kind of stayed the same. And then your sixth one kind of stayed the same. So, but weren't you just adding more and more and more and more and more sodium bicarbonate to the vinegar?
Yeah.
So what do you think happens?
There wasn't more vinegar for there to be more reactions with the.
So we ran out of vinegar. We didn't have enough vinegar for the reaction to keep going, right?
Yes.
Can I ask you something? How many of you guys did the experiment afterwards? You're just so damn curious. You're like, okay, so I have all this damn vinegar left over. I'm going to put half a cup of vinegar in there, and then I'm going to put the 18 grams of sodium bicarbonate in there, because I know you guys had a whole bunch of sodium bicarbonate left over too, right?
Yeah,
How
I
did you
something
know
like
that?
What was that?
How did you know that, Dr. Henry? I still have sodium bicarbonate left.
Because I'm psychic.
Ah.
Because I did all the calculations of how much you need to buy in the beginning. Believe it or not, these things are planned, usually. Speaking of planned, you guys want to do an experiment today?
I mean, it is Tuesday.
Tuesday, right? So let's talk about how you determine your limiting reagents, and then I'm going to have you guys get a couple of things for me. So did you guys go out and get the yeast?
The bread
Yep.
yeast?
The bread yeast, yep. And then you're gonna need to get baking soda and you have peroxide, right? Not baking soda, sorry. Yeast, dishwashing soap, and peroxide.
Oh, I was hoping you were gonna say fruit.
Wait, Dr. Andrew, I think this experiment sounds familiar.
Yes, it should.
Is it the, no, I don't want to mention it, not right now.
Okay.
I'll reserve it for later.
And if you have an empty soda bottle, this would also be another one that you may want to use an empty soda bottle for. Only thing, if you have a big bottle, that might be even better. Okay.
Do we need to be outside to do this lab?
I would at least get the pan. You know, do you guys have your tin, your pie tin? Yeah, grab that. Grab your pie tin because it's gonna be messy. I promise you.
So you said yeast, the peroxide?
Yep.
And a bottle?
And
No
then you're gonna need a little bit of warm water, not hot water, warm water. Okay. So because we need to activate our yeast.
Any measuring cups?
Yeah, let me pull up the experiment. You're gonna need to measure how much peroxide you put in there. Hold on. Let's see. For some reason, I can't find it in your I have to find the lab. For some reason, I don't have the lab listed in your lab reports.
So you said yeast, peroxide, dish soap,
Mhm.
measuring cups.
Yep. Warm waters. And do you guys have conical tubes? You got a 50 ml conical tube?
The tube that came with our packet?
Yes. Yep.
Yeah, I believe so.
Okay, so let me put the lab up. For some reason, it's not showing. Okay, I'm gonna put the list on the board and then I'll give you guys a chance to get it. So you guys don't have the first part. So if you have a water bottle, an empty water bottle, that'll work for us. And your conical tubes will work as for your graduated cylinder. So you should have a 10 and a 50.
What's the lab diaper?
You guys don't have that because normally I have these little packets, these really fancy packets that had a lot of stuff in it, but they cost a lot to kind of build and time to build it. So that's what that normally is. And so a lab diaper is just it's just a sheet of paper. It's kind of like a puppy diaper, you know, the paper that you put down
Yeah.
for puppies to poop on, you know.
And is food coloring, is that our Kool-Aid or just no, ignore that?
You can actually use your Kool-Aid for that if you want to, just a little bit though, because you need to save it for one more experiment. Yeah, one more experiment to do.
I bought 20.
You bought 20 packs of Kool-Aid?
Yeah, I had like, oh, you know, when I was buying it, I was like, I thought about my childhood. I was like, why not?
So instead of a stirring rod, you can use a little knife, a little butter knife. So just something you can kind of stir it. And what you're going to do is kind of stir your yeast, or you could just shake it, put your cap on it and just shake it up. Yeah, there's so many things that I miss about lab, you know, all of the tools and stuff in lab that you have and you kind of take for granted. I mean, although you have similar tools at home, you just got to think about, okay, so what can I use in this case? Right. And so you guys are going to be using, so it says 2 grams of dried yeast. So that is a little bit more than a fourth of a teaspoon, right? Because a teaspoon was 1.55 grams. So I'll make the adjustment real quick and I'll put it up so you guys will be able to see it.
Dr. Henry, just to make sure, you'll be here for the evening lab, right?
Yep.
Cool.
Does it matter if our hydrogen peroxide is 3% instead of 6%?
Yeah, in that case, you're going to add twice the amount.
Got it.
Yeah, back in the old days, we could give you more concentrated one. So. Oops.
Instead of using 30 milliliters, we'll use 60, right?
That is correct.
Okay.
They're asking, are we doing the lab today? We are doing the lab today, right?
That is correct.
They're asking in the chat.
Oh, yes, we're doing a lab today. We're doing it right now. Okay. Let's see, what lab is this? It's lab number 10. At least track.
Doctor, I can't find my yeast packets. Are you gonna be doing it tonight too?
Yes, I will be.
Okay, then I'll come back for that one then.
Dr. Henry, what if we don't have like a 100 millimeter graduated cylinder or a 10 milliliter graduated cylinder?
Okay, so what you're going to use, you're going to use your 50 mil conical tubes and your 10 mil your 15 mil conical. I'll change that real quick. So
Both of my 15 mil tubes have deionized water. So is it okay to just dump one?
yeah, go ahead and dump one.
Okay.
And Professor Henry, I have a question.
Yep.
So for the hydrogen peroxide, what do we get for that?
It's hydrogen peroxide. You should have bought it when I gave you the list of things to buy. It should have been on that list at the dollar store.
Oh, then it must be. Yeah, probably. I'll look for it now. Probably it's in my boxes.
Okay.
All right, now okay, for
No
sure.
problem.
When is that lab due?
It's due next week.
So we're just doing the lab this week?
Yeah, we're doing the lab this week. The lab report will be due next week.
Okay.
Okay, so I have to make some adjustments because I'm using the 50 mil.
Dr. Henry, so when you were on that phone like conference call earlier, we kind of brought this up. So the last week's lab is due this Friday. You're not pushing that one to like Sunday or something, because since not the practice exam, but since the exam is due on Friday as well, and as the practice exam, is there going to be like a little more opening for the practice? I know I'm asking a lot in one.
So technically, there should be 20 attempts on the practice exam.
No, but it closes, like it says close tonight.
But yeah, I've extended it. It should be extended. If it hasn't extended yet, I'll fix that. Let me see. It should be extended till Friday. So.
But so everything's still on Friday then, like the lab.
Yep.
With the okay.
Yep. Everything is on Friday.
Dr. Henry, I got a question about the hydrogen peroxide.
Okay.
Is the 6% referring to as the bottle of a hydrogen peroxide or just the?
Yeah. So if you have I'll put that in the instructions.
I have a 3% bottle, that's why.
So then use 60 mils, double the amount. Because what we want is the hydrogen peroxide. The rest of it is water. So it's just water weight. So.
And you said an empty bottle of, Dr. Henry, an empty bottle of soda?
Yeah, empty soda bottle, that'll be good.
What about water?
Or an empty water bottle, that'll be good.
Okay.
Either one. Yeah.
All right, then I will see you at the evening lab, Dr. Henry, because I can't
Okay.
make the one right now.
Should I
Okay.
rinse it?
What was that?
Should I rinse out the empty
Yeah,
bottle?
rinse it out because you don't want any of the soda in there because that'll cause another reaction, which we don't want.
I'll also be back for the evening lab. Have a nice day.
Okay, I'll see you this evening.
Later, Dr. Henry.
Okay.
So Dr. Henry, it doesn't matter what hydrogen peroxide bottle I use?
It doesn't matter. It'll be fine.
All right, because mine says it's 3%, so
That'll be fine, but you're going to use 60 mils of it instead of.
I can use it with the tubes that were in my kit, right?
Yep.
I have only this tube, the 45 milliliters. No, it's the 50.
Let me see what you're showing me. Oh, that one is actually a 50. It's really a 50, even though it only marks up to 45. It goes all the way up to 50. The line at the very top, you'll see a clear line at the very top.
Yeah.
It'll be 50.
Oh, okay. Oh, yeah, I see. Yeah, and that one?
The other one is 15.
15, okay.
15, 1-5.
Okay. Thank you.
And I'm making the adjustments right now so that you guys.
Dr. Henry, is it fine if I can do this lab on my own time?
Yeah.
Okay. So I know Brittany asked you this earlier. So since the exam is going to be pushed back until Friday, which means you won't penalize us.
Yep.
And the practice exam will be pushed back as well then?
Yep.
Okay then. Okay then. Well, thank you, Dr. Henry. Have a good day.
You too.
So we need the scale because I don't have one.
You don't need a scale.
Oh,
You
okay.
can do it without the scale. So you're going to use about 1/3 of a teaspoon.
Okay.
So we don't need a scale now.
Wait, Dr. Henry, this lab is about the elephant toothpaste, right?
That is correct.
I just discovered it now.
Yeah.
All right. Well, I'll see you then, Dr. Henry. Have a good
Okay.
day.
I'm sorry, Dr. Henry, how many milliliters of the 3% hydrogen peroxide? It says 30 for the 6, and how many for the 3?
60.
60. Okay.
Yeah, you want to double it.
So that's like a tad bit over the 1/4 cup.
Yeah. Or you can use your conical tubes. Do you have your conical tubes with you? So that one is 50. So if you get 2 of those, or 10 and a 50.
I just noticed this. What's the liquid already in the tube?
Water, distilled water. So that's going to be.
Oh. So just leave that one alone.
Yep. Okay, it should be up. The lab should be up now.
Hey, Dr. Henry.
Yep.
What can we use for that 100 milliliter cylinder?
So instead of use your 50 mil conical tube.
Uh-huh.
And then and you're talking about where you're going to put everything into.
Yeah.
Okay, so what you're going to use for that is you're going to use a water bottle.
Dr. Henry, for that first step, when it's saying to record the volume on the table, so you're just saying record the 60 milliliters of the hydrogen peroxide that we initially poured?
So you asked me if you're using the 60%, I mean the 3%, you're going to be using 60 mils of your hydrogen peroxide.
Right, but it says record so we're just recording however much you started with?
That's right. How much you're putting in there. Yep.
Okay, so am I literally just, because I put 10 drops of soap in here in the
perfect.
water bottle.
Yeah, that's fine.
So just add these together.
That's right.
Professor Henry?
Yep.
So for the first part, if I have like 3% hydrogen peroxide, I would pour like 10 milliliters into the 50 conical tube.
So you said if you have 10%.
Or I have the 3% one.
Yes. So you're going to be pouring, you're going to be pouring 60 mils, right? So because that would give you the same amount of hydrogen peroxide.
I was just confused. So like the yeast part, I would just put like 2 gram, or I would just put like the majority in the 50 milliliter and then like a little bit in the 10.
No. So what you're gonna do is, so you're gonna use the conical tube to just get your measurement of 5 mil, right? And you have your 50 mil tube, right? You're gonna put your yeast in that, and then you're gonna put the 5 mils of warm water in there, and then you're just gonna mix it. You could have also done it, you could have put it all in the 15 mil conical. That'll work well too. That'll be fine.
Oh, okay, thank
But
you.
it's just a lot easier when I was actually weighing it. It's a lot easier for me to get it into the 50 mil conical tube than it was the 15 mil.
Oh, okay.
Yeah, because otherwise you get it all over the place.
Okay, so Dr. Henry, so I have all the liquid parts into the bottle.
Okay.
For that 2 grams of yeast, you want me to add it to the tube and not directly to the bottle?
You're gonna add it to the tube because you want to get it activated first with the warm water.
Okay.
Dr. Henry, when we're doing the experiment, if we're doing it in a water bottle, could we just like swish it around in the bottle instead of stirring it?
Yes.
Okay.
Nothing happened, Brianna. Let me see your screen.
I put it in here, but like it didn't like foam up or whatever. Oh, kind of, not really though.
Okay, so let's see. So you put, how much did you put in there? That's a lot.
Well, it's starting to foam up now, actually, kind of.
Okay.
But I just
So did you activate your yeast? Because your yeast has to be activated with warm water.
Yeah, I activated it and then I poured it in there.
Okay. Do you still have some yeast in that conical tube?
In the tube?
Yeah. Is there like a lot of it left?
No, there's like barely any left.
Okay. No, your 50 mil conical tube is your 50 mil conical tube. Your soda bottle is going to be what you're going to be putting everything in.
Dr. Henry, for that record volume before reaction starts, are you talking about the volume of the yeast before we add it to the bottle, or?
No, so like mark on the bottle where your volume is starting at, okay?
Oh, okay.
And so before it starts foaming up, and then you want to mark after it foams up where it's at. And then what you can do is, if you do that, you can actually use water, you can fill it up, and then you can use your conical tube to get the actual volume of it. Does that make sense?
Once the foam's gone?
Yeah, well, you want to mark, so you mark where you started from and you mark where you end. And so what you'll do is just you can put water up to that point, and then you just pour that volume into your conical tube to calculate your total volume.